Okay, last notes for this chapter. Oh yeah, unfortunately, I've got the previous chapters up there. I believe it's chapter 5 with your current textbook, but it's still the same. It's actually the same book, they just did it differently in different years, so your test will be on chapters 4 and 5, or energy and thermal energy. Okay, so let's talk a little bit about heat transfers. I was going to say the most common way of transferring energy, but this is probably one you're more familiar with, even though it's less common when we think the whole universe, is conduction. This is transfer of energy with no transfer of matter, but the things have to be touching. So if you're playing a game of hot potato where you have a hot potato, which has high specific heat, so it stays hot, and you toss it from person to person, that's not conduction, that's just moving an object. But if you reach out and touch the potato and say, ouch, it's hot, that was conduction. When conduction happens with gases, it's really, really slow. There's low density, all sorts of reasons. With liquids and solids, it's much, much faster. Think about hot air in a room, not blowing in your face, that's convection. But if you walk into a room and it's hot, okay, now stick your hand in hot liquid or put on a hot solid, and you notice that the transfer is much, much faster. What's going on here is the bottom left molecule right there is receiving some sort of thermal energy, and it bounces the particle vibrates faster and faster, so it bounces into its neighbors more often, and they bounce in. So it's kind of like having a bunch of molecules there, and you suddenly put in a bunch of energy, and it spreads very, very rapidly because the particles are so close together. Things that conduct thermal energy well are called thermal conductors. Metals are good thermal conductors. These are things where the energy moves from one part of it to the other. The top picture there is a spoon, and I mean, you'd have to look up the colors and figure out exactly what the temperatures correspond with. But it looks like the white and the orange is hot, and the blue is going to be cold. These are just false colors that they put on for different temperatures. And the spoon is fairly cold, but when you put it in there, you'll notice that it gets hotter than the pan, at least for right now, because it's conducting heat from the bottom of the pan where the flame is touching and going up the handle. On the opposite end, we have thermal insulators. Now, you should never say an insulator stops it from conducting, it just conducts it very poorly. It'll still conduct, just really, really slow. Air is an excellent insulator. We have the double pane windows with air between each pane. That is an excellent insulator. Unless you have convection or something in there where it's getting mixed up, the air just sitting there quietly does not transfer the thermal energy very, very well. If you have one of those blankets that's knitted and has the holes in it, crocheted or whatever, and if you put it between a sheet and a quilt, then you trap air pockets, and that insulates better than if you put the blanket with holes in it on top of the quilt. You have, feathers. You have all sorts of different objects that have these air pockets in them. The top right one looks like, it's a hard picture to tell, but it looks like something called aerogel, which is mostly air. And the solid parts of it, I mean, it's just, think of it as like a mega fluffy marshmallow with air pockets in there. But it'd be much, 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 much lighter than a marshmallow. It's developed by NASA. It's actually really neat stuff. There's this really cool thing called I think it's called the Leidenfrost effect. And if you are cooking, you can throw some water droplets onto a skillet, and if the water droplets just sizzle, the pan is not hot enough yet. If they sizzle and bounce around and skip all over, then you've got the right temperature. What's happening, or you've got hot enough, not necessarily the exact temperature. What's happening there is the bottom of the water droplet is vaporizing, and that basically means the water droplet is hovering on a cushion of air, a cushion of steam, and it allows it to bounce all over the place, to scoot around on that pan. Don't try this. But apparently, this is the effect that allows you to walk across hot coals barefoot. If you are nervous and you're sweating and your feet are sweaty, which doesn't, I can't relate to that, but maybe they do. I don't know. Maybe it's just enough that the bottoms of your feet get this Leidenfrost effect, where you get the steam right there at the bottom, which is a very poor heat insulator, and a very poor heat conductor, good heat insulator, and it allows you to walk across those coals as long as you do it quickly. I know Adam Savage from Mythbusters did a thing where they tested this out, where supposedly you can take your finger and dip it into molten lead, which is like over 900 degrees, and be fine. They didn't do it with their fingers, they did it with a hot dog, and it was the Leidenfrost effect. And if the hot dog was dried out, not a chance. But if they wet it first and stuck it in there, they'd put it in briefly, take it out, and the hot dog was unfazed. Don't go try that, okay? All right, we have convection, which is a transfer when the particles will actually move. So when I said the hot potato being passed around, that's not conduction. Well, that's closer to convection. It's where the particles are getting moved around. Now, what's interesting is when you heat stuff up, okay, sorry, I just got distracted. Dog walked in and she's covered in grass and mud. I may have to pause this. So the thing, when it says heat rises, okay, that's true, but here's why. When let's start again. So in that statement it says when heat rises. That's true, but there's a good reason for it. As things heat up, they expand. We talked about that yesterday. As gas particles, so think of the air. If you heat up some air, it expands and becomes less dense. More dense air or colder air pushes it upward. So that's why heat rises. Okay? So as it rises up and up and up, it's going to expand more and cool down, and then it becomes more dense and sinks to the bottom, and you get this circular pattern going on. You have what are called convection currents. So this loop of it heating up on the bottom, cooling off at the top, and going back down. A lava lamp is a perfect example of that. On a much bigger scale, we have ocean currents. We have our weather systems. Earth's interior does this. It's hot, and magma comes up to the surface, cools off, and sinks back down again. Hence, earthquakes, volcanoes, that sort of thing. Okay? In the whole series, okay, so there's good animation of it, whole series of pictures here. I should have found a better picture of the sun that has the diagram, but in the very center of the sun, you have the core, which is just incredibly hot. There's actually no convection there. And the outer part, where there's no, well, there is, no, wait, I've got it backwards. Convection zone is on the outside of the sun. And, okay, I got to go find an animation for this. Wow. Okay. So what you're seeing here is an ultra close-up of the sun. And these are called granules, those little granules, those pieces of the sun's surface that you can see, those are about the size of Texas. And what they'll do is they'll rise up to the surface because they're hot. They cool down at the edges. So the edges are actually black because they're a little bit cooler. Several thousand degrees cooler in some cases. They're still they'd be too hot to touch, but it's cooler than the rest. And then the whole thing sinks down. And these Texas-sized granules take about 5 minutes to do completely. It is Really, really neat what the sun does. And I started from the beginning, not where we were. That's what I get for doing this and talking. Okay, you've seen water boil on a stove. That's a glass one. Don't try that at home. You have to have the right kind of glass to do that. This right here is a picture of probably an infrared of candles on a birthday cake. And you can see the convection, the turbulence goes up very quickly and then it slows down. It's hard to see the loop in that one though, but it happens in everything. The last thing we have is radiation, which is simply waves moving through space. It's nothing dangerous. Yes, there is some radiation that is dangerous, like gamma rays. Those are lethal. Those can be lethal. Everything emits energy. You emit energy. You are emitting energy in the form of infrared radiation, which you could pick up on a thermal camera. The little temperature probes that everybody's holding up to your forehead this last year, those are measuring the infrared radiation from your forehead and figuring out your temperature based off that. So you know this. If you have lots and lots of infrared, you can feel it with your skin. You don't need an instrument to say, oh yeah, there's some. You can feel the heat from a grill or a heat lamp without any sort of thinking about it. And there's some nice little pictures for you. Okay. We also have thermodynamics. Okay. Thermo means thermal energy, and dynamics means movement or motion. So we're talking about how thermal energy moves around and going from one thing to another. That's a conversion. So the first thing that you need to remember, and by the way, there is a zeroth law, but I'm not going to get into that. It's one of those, they came up with the 3 laws of thermodynamics and then realized, oh, we missed one, and it's really, really basic. So yes, they literally call it the zeroth law. Google it if you want. But the first law says energy can't be created or destroyed. So if I turn on a flashlight, that energy comes across as radiation, invisible light, and that visible light will strike a surface and eventually turn to heat. The energy is still there, it's just in a different form. The next one says that everything goes from hot to cold. You never, ever, ever put an open can of Coke on the counter and it's, maybe 75 degrees in the room that you're in, and all of a sudden the Coke freezes. No. It's going to go from whatever's hot to whatever's cold. So if your Coke is cold, it's going to warm up in a warm room. Okay? If you have a warm Coke in a cold room, it's going to go from hot to cold. The Coke would get colder. They would meet what's called equilibrium. And we talked about absolute zero. Absolute zero technically can't be reached because you have to stop all motion. And when you're dealing with protons and electrons, you can't stop them. That's just beyond nature. The lowest ever recorded is actually, I've read lower than this. It was around a millionth of I'll say degree, even though it's in Kelvin. What they do is they hit an electron or a particle or an atom with lasers in multiple directions, and they basically pinch it and squeeze it and try to hold it still. And they measure the motion, the vibration of that particle, and then through fancy math, you figure out what that temperature would correspond to. So yesterday you did some conversions between Fahrenheit, Celsius, and Kelvin. And this is a great, great picture on that. I said that absolute zero was 454 below 0 Fahrenheit yesterday. No, 459. 454, I think that's actually where liquid helium is. It's a number that's always stuck in my head, apparently the wrong one. But yeah, take a look. If you look on the Celsius and Kelvin scale, you'll notice the numbers go up the same amount from absolute zero to freezing, it goes up 273. And then from freezing to boiling, goes up 100. So Kelvin kept the exact same scale as metric, but he just chose different numbers. Fahrenheit is just, yeah, you'd have to add 32 and then multiply by 5/9 or 9/5 or something like that, because just a totally different scale. Okay. There's this thing called a heat engine. That does not mean your engine is hot. Okay. A heat engine is anything that takes thermal energy, causes movement out of it as the thermal energy transfers from hot to cold. Believe it or not, you can do this with electricity. There's what's called a thermoresistor, and if one side of it is hot and the other side is cold, the flow of heat through this thing, this thermoresistor, will actually cause an electric current. And that's exactly how the nuclear reactors work on, like, the Mars rover. They have a small amount of plutonium in the rover, and it heats up one side just by natural decay, just heats it up. And as it cools off, it does it through the thermoresistor, and that generates the electricity. Now, what's crazy is that the Mars rover uses less electricity than a hairdryer. I mean, it's like a couple of light bulbs kind of electricity, very low. So they will literally have to say, okay, we're going to use our electricity for driving today, or we're going to use it for moving this arm and taking pictures and that sort of thing. You don't have everything powered up at once, and you got to be very careful with it. With a car engine, you are taking thermal energy, and through expanding gases, these explosions inside there, or diesel, it's just a burn, not an explosion, and you are converting it to mechanical energy. You are making movement out of it, which eventually finds its way out as heat through friction. So yes, an internal combustion engine of a car is a good example of a heat engine, not because it's hot, but because it uses thermal energy to get some sort of use out of it. Okay. On your guided notes, I'm going to put a list of things up here, and just put either whatever works for you. Conduction, convection, CD, CV, or R. If you want to abbreviate, you don't have to. So on your guided notes, you're going to write these down and list it out as either conduction or convection. And you're going to want to pause the video now so you can see those, because I'm going to end it now.